It's the SDG Podcast. Before we get started, you can check us out on the web at solutiondesign.com/podcast or find us on all the social medias, LinkedIn, Twitter, Facebook, and Instagram at Solution Design Group.
It's our 100th podcast. This is 100.
This is 100?
Yeah.
Okay.
Yeah. We're not going to talk about our 100th podcast or
the first rule about the 100th
This is 100.
Is don't talk about the 100th
We
podcast.
can't look back on 100 podcasts when we're doing the 100th podcast. So instead we're going to talk about quantum computing and try to understand. I'm going to try to understand it. And you guys are going to try to explain it to me.
All right.
I'm hoping. But first we want to celebrate a little bit. That's why we're after hours having some adult beverages. We've checked IDs. Everybody's old enough.
Mine's fake.
It definitely isn't 10 a.m.
It fools me. All it's got to do is fool me. So, Dan, you want to do the honors?
I will do the honors.
Excellent. Here it goes.
Which way are you going to point that?
We do next.
A window.
Straight up.
Fluorescent light.
Whoa! Almost got it.
Almost.
Without knocking over your beverage. Excellent.
There was
we're going to
no
have a little toast, and then we're going to get into quantum. All right.
All right.
Cheers. Here's
Do the same.
All right.
Here's to 100. And
Nice
maybe
work,
have
nerds.
100 more. Quantum computing, I keep hearing that this is going to change everything. It's going to break all the world's encryption.
You're just going to have to change your password.
Yeah, instead of 12 characters, it's going to be 12 million.
Instead of the password, the word password, you're going to have to go with something a little bit longer. Maybe an exclamation point or something.
Only have room in my head for one word. And it's got to be 12 characters.
You can use the @ symbol for the A.
That's genius.
We'll teach him leet speak.
All right, so quantum mechanics is not something that's easily explained.
Actually, Dan, it's not that hard, right?
It's pretty much impossible to talk about quantum mechanics with English words, is what I've discovered in decades of trying to understand it.
Decades?
You can describe it with math that's way harder than probably anybody in this room is familiar with.
We have a whiteboard.
I don't know the math. The best we can do, I think, is to use inappropriate metaphors and misleading analogies.
Perfect.
So,
Yeah.
All right, give us an inappropriate metaphor.
Inappropriate metaphor. Okay, well.
So there's birds and the bees.
Well, so everybody knows about the cat, right? Everybody knows about the
Classic
cat.
Schrodinger's cat.
You put the cat in a box, you have a quantum event, which has a 50-50% chance of going one way or the other. In quantum mechanics, we say that radioactive event, they usually use some sort of a radioactive material that decays at a rate of, it has a 50-50 chance of decaying or not. So they'll say that radioactive isotope is in a superposition, meaning it is decayed, it's not decayed, it's decayed and not decayed, and it's not decayed and not decayed. So, like I said, words don't really work too well. But the idea is, does that mean the cat is dead and not dead and not dead? All that kind of business. What it means for quantum computing is that instead of having a 0 or a 1, you can have logical units that are in superpositions, which give you a lot more computing power, it turns out.
So instead of 0, yes or no, you get yes, no, and a variety of maybes in between. And that actually lets us do so much more than just...
Right. So there's bits in normal computing.
And qubits.
Qubits is what they call the logical unit of computation in quantum computing.
And the reason why there's only two options, yes or no, the reason it's binary is because at the core of every computer is the transistor that basically is an on-off switch, one way or the other.
Every program that anybody in this room has ever dealt with is run on a von Neumann architecture, which is the processes.
You got to enunciate that first word a little bit better.
Von Neumann.
Von Neumann.
Architecture, John von Neumann. You can look him up. He had a lot to do with our modern transistors. And any program you've ever dealt with is just a sequence of logic gates that are either on or off. And it turns out if you string 1 billion of these gates together, you can solve there are problems that are too big, this particular architecture, and that's where quantum computing promises to enlarge the computing space, I guess is the way to think about it. They talk about adding additional dimensions. So you can have a multi-dimensional computational space. So think of it like, what if you had to do all your computations on a sheet of paper, and once that paper's filled up, you're done. And so anything you can't solve by you can try writing smaller, you can do all sorts of things, but you're going to hit a limit. Quantum computing promises to Like, suppose you blew that sheet of paper up into a 3-dimensional room, and now you could use an entire room, computational space. It's kind of like not
You can
really.
almost think of it as like we've been drawing on 2D paper all along, right?
Yeah.
Here's basically that, right? And all of a sudden we're adding a holographic dimension to that. So instead of just measuring a plot on a chart, you can measure a plot and a depth and a luminosity and all these different factors to that thing. So I was at a talk at reInvent last year where they were talking about quantum computing, and they were actually talking about like physicality of how they actually do this. And the technology is amazing. Like they literally measure atoms, right, and cells and nuclei. Like they're exploring all these different ways to measure a qubit, right, to actually get that yes, no, maybe answer in between. And it's actually fascinating. There's a couple different there's a lot of different implementations of the actual quantum computer itself, and some of them are down to the cellular level. It's just measuring the size of the nucleus, or measuring the size of the membrane around the cellular level, and saying, "Hey, this may be answer right in the middle." There's some that deal with. Oh my God, there was a talk by a physicist, and she was talking about optical tweezers, and it just blew my mind. Like they're literally moving around bits with these lasers and measuring that, and the actual, like, there's not going to be like a CPU like we're used to, right? There's not going to be a quantum chip that Apple's got.
Intel's actually working on silicon-based transistors and silicon-based qubits that can fit into an architecture. But it does introduce its own problem. Qubits, as they are incredibly unstable. So like as it is, we're talking about things that are very, very small, and they're very, very different in their environment. So in these, things like heat, other qubits around it, really anything, just a magnet nearby enough,
Right.
will be something to give it an error where it's either a phase flip error or a bit flip error, where it's just like throwing off what the recorded data.
Okay.
We're not going to have that in this though. Like that's not going to be a thing.
Not for a long time.
Not until
What you're talking about is called decoherence. It's the term of art in quantum mechanics. And in order to prevent decoherence happens when a quantum system interacts with some other environment, which can be almost. And so one of the things they have to do with quantum computers today is they have to supercool them down to almost absolute. Absolute zero is the coldest anything can get. And if you remember a little bit from physics, what we measure as heat is really just the motion of atoms. So if something is hotter, it just means the atoms in that substance are moving faster. Quantum mechanics says you can never get anything to absolute zero, because at that point you would know both the position and the momentum of the particle. And quantum mechanics doesn't let you do that. So you can get it almost there. And that's what they have to do for these quantum computers. And in order to do that, you need a machine as big as a RV or something to cool it. And so most of a quantum computer, the physical structure, is a cooling apparatus right now.
Yeah.
you're starting to sound a little bit like Bill Gates.
Now-
You're never going to need more than 8K of memory.
There was
You're
this,
never going to need anything less than a room to run a quantum computer.
There was this thing they did to make a room temperature
superconductors, yeah.
and it turned out that
They got close, right?
they did get close, but
They
not-
updated it saying that part of the outside film of it is superconductive, but not the rest of the material itself.
right. So that would have changed the game for quantum.
It would, because the superconductivity is something they rely on for quantum computing, and that, as far as we know, is only possible at super cold temperatures
Right.
now.
Do we believe it, or have we only just produced, like, theoretically it's possible at all temperatures, right? Because just like fusion is possible at all temperatures, theoretically, it just doesn't seem to happen. Things
Yeah.
other than 10 million degrees centigrade, right?
Yeah, I think the problem is the whole decoherence problem, because like a lot of people have heard in the popular science this whole idea with a quantum experiment that if you look at it, you're going to get a different result that if you don't look at it. This is called the measurement problem.
That's
we're
a
not,
whole
we're not going to get into it.
Yeah.
But what is a measurement? That's the measurement problem. It can be just some little molecule bumping into can decohere. So I think that's where, like, the only way we know how to minimize the decoherence problem right now is through supercooling.
Okay.
Not entirely. There's also Microsoft that's working on topological qubit, which is taking a specific type of material that only exists in a 2D plane and then tying and braiding multiple of those together to essentially get a qubit that's made out of dimensional strings. And then that essentially acts as something where it's like you have this string that has a knot, and no matter how you rotate it, how you stretch it, how you compress it, it ends up staying in that knot. And the mathematics around that are pretty interesting. But it does introduce its own limitations, and it's still really hard to make these things. It's hard to scale those up into larger systems.
I love that the company that can't make software that will stay open all day, Teams, is doing doing that, right? Like, all I really want Microsoft to do is stabilize Teams so that I can be on a call for an hour without it dropping.
Teams for Mac.
And instead, they're like, you know what we should do? We should tangle up some Qubit. We should do this.
Have you tried taking your computer to a walk-in cooler during Teams calls to see if that helps?
I've tried
Super cool.
things. And you know what I've
Just some
tried that
liquid
doesn't work?
nitrogen.
Yeah.
Yeah.
Throwing your computer doesn't fix the problem. I've figured that
Percussion
out.
maintenance will, I promise.
It will change the problem. It just may not necessarily solve it the way that you were hoping.
So the quantum computer, if they build it and it works,
They have built
They
it.
have
Yeah.
built it.
It's
they
just-
built it and it works.
Simple one.
Yeah, they're small, limited. There's problems with the coherence time of how long the qubits stay in motion or like stay in the state that we expect them. And there's limitations on scaling that up to a point that it becomes applicable in the real world.
Okay.
And there's some companies that have made some progress on that, like Google in 2019 put out a claim of quantum supremacy that they were able to like optimize a problem.
That sounds like an Avengers movie.
The quantum supremacy.
Don't give them any ideas.
Ant-Man 4. Quantum supremacy.
Matt Damon will be in it.
But they were trying to solve some problems, and they said that they were able to more efficiently solve, this very specific, hyper-mathematic, very unquantifiable in human language problem for optimization with a quantum computer that beat any existing supercomputer that tried to do it faster.
Is this like your high school friend that had a girlfriend but she lives in Canada? Like, yeah, no, we solved this problem. It exists, and I can't show you, and she's never here.
One or two of them had to exist, right?
I'm a
Or
little
is that
bit
the-
tired of you all questioning my girlfriend.
Or is that the Schrodinger's cat girlfriend, Canadian girlfriend?
Is she here or is she not here?
Yeah.
Is she alive or dead?
The way I think of the Schrodinger cat thing, because it's hard to get your head around, because it's like it's in a superposition, meaning that you don't know if it's alive or dead. But it's
could
not
be
like it's not really the fact that you don't know. It's the fact that it's both alive and dead at the same time, and you don't know. And once it's observed, it's gonna become. It's going to no longer be in a superposition. It's going to be a specific cat. It's going to be that cat's alive or the cat's dead.
So you just outlined what's known as the Copenhagen interpretation of quantum mechanics, which
I feel like I'm playing chess with somebody that knows that all the openings
what
are
you
full.
just said is the Copenhagen interpretation. What the Copenhagen interpretation says, and this is the original formulation of quantum mechanics that Einstein didn't like, but it goes back to 1905. It says that it's not that we don't know, it's that it really is in a superposition, and then as soon as we look, the wave function collapses, and and there are other ways of it. This is about, so the math works. The math behind quantum mechanics works. What it implies about our world is what's up for debate. Some people say the wave function collapses. Hugh Everett, proponent of the many worlds interpretation, says no, it doesn't collapse. It just branches the universe. And you're in a universe where you gotta know, but there's another you in a universe where you gotta yes.
So I've got a more practical application of the Schrodinger's cat. It's so if I'm at a bar at midnight and I don't look at my cell phone at all, I don't know if my wife is mad or not.
Exactly.
Right? The minute I look at my phone and see 30 text messages,
You'll have determined.
I will have determined, oh, yeah, she's a little mad. All right.
I came up with my own interpretation yesterday when I was brainstorming about this.
Schrodinger's happy hour. That's what I call that.
Somebody makes some Kool-Aid and that's in front of you, and they use sugar and water and flavoring. So it could be watered down, it could be bitter, or it could be sweet, but you're not going to know until you taste it. So your Kool-Aid is a superposition until the wave function collapses because I drank all of it.
The wave function is the Kool-Aid entering your stomach.
Have you seen any of the actual services that are providing quantum computing? So AWS has a thing called AWS Bracket, right? It's this whole, they actually will let you run applications or you can run your Jupyter Notebook against an actual quantum machine.
Right.
But before you get to that point, because that's really, really expensive, they actually have, they have this whole process, right? So you write out your notebook or whatever app you're going to run against this thing. And then your first step is actually a simulation of a quantum environment instead of an actual quantum computer. And then it gets to the run phase where you're actually wanting to run something against a quantum computer, but it's not as simple as like firing up an EC2 instance, right? Like they've actually got to reset that thing for you, right? So it's not an on-demand like, hey, I'm going to spin up an instance, I'm going to throw it into a Kubernetes, whatever those kids call it.
So somebody runs out to the floor and they flip the switch to reset the server and say, all right, now it's Chad's.
There might be a Mechanical Turk involved, yes, potentially. I don't know that there's not, but there's an actual service where, like, if you really wanted to play with this stuff, limited to academics, really.
There's several services, including, I don't know, I bopped around yesterday and found one that's free. Oh, somebody's got their notes. We'll find out soon.
Rigetti Computing is a company that's been around providing processors and cloud services. IBM has a few things.
IBM, I think, was the one that had sort of a free plus, and then
So
here's
all
our
the free stuff
127 qubit machine, right?
All the free stuff I've seen is all simulations, mostly, right? Like they're not going to like actually reset
Right.
a thing for you because you want to say hello world in quantum computing.
Correct. But like that's not even necessarily the programming that you'd present to it, because you wouldn't necessarily have like the software we have in between our transistors and our like software now. Like we have Microsoft and all the ways that we can program, Windows to do stuff to then drive, a specific architecture. Right now where we are with quantum computing is there's a lot of like, I'm presenting you with a mathematical problem of like a huge data set to try and solve, It's like all still very mathematical. And there's not necessarily like a, service.get, environment variable and programming that way. It's not necessarily built or structured around that. There isn't necessarily the software doing that kind of programming with
Dan's got something on his phone called the Universe Splitter, and I'm a little terrified.
Yeah, have you seen this? So this is an app you can get for your phone. I think it costs $1. And this is actually, I forget who's behind it. It's actually hooked up to a real quantum system. So you can take a chance or play it safe. So the premise behind this app is when you put something in here, say, should I go to a movie? When you submit that, it actually goes off to a system that measures an actual quantum event. Let's say it's a radioactive isotope. Mm-hmm. It goes and looks, did the thing decay or not? If the many worlds interpretation is true, at that point, the universe forks. And there's one universe where you go to the movie and another universe where you don't go.
So you're completely forked, is what you're saying.
That's the many worlds interpretation. And it's actually got a following among Sean Carroll's a contemporary physicist. I've read a lot. He's got a lot of books for popular science readers. He's a proponent of it. He wrote a book about it called Something Deeply Hidden. It's I don't know if it's mainstream, but it's getting serious press in the quantum mechanical literature.
Really quick question about the many worlds interpretation of this. How the hell did I end up in the best possible world? Right? Like, there's so many infinite worlds out there.
You're in all of them.
I'm in all of them, but the one I'm in right now is the best. Like, there's a hot dog straw. Oscar Mayer is making a hot dog straw.
Yeah.
This is the best timeline
What
that you could possibly be a part of.
Baked beans? What do you drink with that?
Bloody Marys, all day and all night, baby. Yeah.
There's also a world where you're languishing away in a gulag because you got caught with an illegal hot dog straw.
What?
So that's pretty wild. So, like, here's the thing, though. Is it only many worlds in that all these quantum events, sure, we're doing this and we're monitoring a quantum event through now having done this. Is it just as easy to say that whatever quantum events that are happening just in nature ambiently all the time are just happening and also still branching off?
Yeah, of course. It's the measurement problem. Is it a measurement if I have a quantum system and then like a stray photon leaks through and bangs into it? That could cause decoherence. Does the universe split then? I don't know. It's up for debate. Nobody really understands the measurement problem.
I mean, it's kind of the infinite number problem way back in whatever grade you learned about infinite numbers or, pi or things like that. Like imagining that forever on all the things infinitely in all directions just becomes really hard to...
We don't really have the hardware to really make sure what reality is really like.
Right.
If that's the case, I don't think we have the hardware to...
Sure.
I have a camera on my phone.
I mean, the Matrix did it.
Yeah.
They were using weird symbols.
They had so many human batteries to charge that thing, though.
So the quantum computer, let's say it's finished, It's ready. It's good. It does it all. An RV in a parking lot we can all plug into and use. What are we going to do with it?
Biggest things is optimization, cryptography. It does those things better than classical computer exceptionally well, at least for what we found so far. I'm interested to hear your interpretation on that.
It could probably model weather a lot more accurately, I'm guessing. It'll definitely upend the whole cryptography industry because right now everybody relies on the RSA crypto system, which so RSA is based on the idea that if you have this huge number that's the product of two prime numbers, which are also huge, figuring out which two prime numbers produce the product is very, very difficult. And even with all the computing power on the planet, it would take like millions or billions of years to crack some of these passwords. But with quantum computing, there's this idea that rather than brute force this thing, which would take forever, what if you could run all possible solutions in only the correct one? So cryptography will be out the window. Our modern cryptographic systems.
RSA was put in 1997 or 1977, excuse me.
Yeah.
So that's not necessarily modern, but like that's what we're using.
It's still used on the web.
Well, yeah, it's used everywhere. It's the basis for all of our web encryption. And I think that the encryption of some of the ways that they're trying to harden against quantum computers is really in with like making lattice-based problems around things like that.
Yeah, but I mean, I don't know. Like Yogi Berra said, predictions are hard, especially about the future. Right? And so anything we say, I thought cameras on phones were the dumbest thing I ever heard of. So I'm like, that's never going to be a thing.
Right.
I'm not
The
going to.
Polaroid knew that like way ahead of time with the S600. They were making a handheld camera that you could fit in a coat pocket, that you could have wherever to just capture a moment in time.
Yeah.
And we as humans value our memories so much, I think that was a great idea.
Yeah.
And it was just a natural evolution to put it on every device that we have that now has every single sensor that we need on it, gyrometer, fucking accelerometer, like everything.
I liked photo.
I apologize, Emily.
Get film developed. So we're not like regular computers are not going to be replaced.
No.
They won't be replaced. There'll probably be some kind of a hybrid thing because, again, you can't carry around a quantum computer in your pocket because of the decoherence problems.
Yeah.
So it's going to be like something in the cloud, a cloud service that's tied in, and anything that needs quantum goes out.
I would think so.
The answer gets turned in. Okay. What can't quantum computers do?
I mean, that's not the right question, I'd argue.
Well, I don't think you asked the right question.
So that is a good question, but a better question is there any applications where quantum computers are going to be better than conventional? Because it can, essentially, it's still processing information. It just now has the capability of processing more information.
Right.
But with all of the limitations of it, why introduce this as a thing to do? Like blockchain, it is a technology, it does things, but why use blockchain to manage, your database if it's a less efficient means of managing than just SQL or something like that?
But think about all the stuff that we've been talking about lately. AI, right? AI is just one huge math problem. All of the neural nets, all of that math happens.
It's a large amount of data and a large amount of computation.
A large amount of data, and it's the computation that quantum is going to help with, right? Because right now, we basically have to do all those calculations sequentially, right? On binary computers. And we use GPUs instead of CPUs because the parallelism. Wow, thanks, Grable. I wasn't able to. I didn't get that. Because the parallelism on GPUs is so much more efficient than on CPUs. But with quantum computers, you're going to exponentially blow that up, right? So AI and any kind of data model, any kind of mathematical model that you're going to produce is going to get so much more efficient using quantum computing than if you just use the paradigms that we're used to today. That's probably practical purposes what everybody can kind of latch onto today. That's going to get exponentially better and potentially scary soon.
I think I agree with you because one of the other problems I'm really interested in, just as a curious human being, is
you can full on agree with me. It's okay.
Kind of the mind-body problem, right? It's still, so for centuries there was this debate, like where does the mind come from? How does it relate to the body? Modern science is pretty close to saying, well, it emerges from electrochemical activity in the brain. Consciousness arises out of that. It's not something separate. It's a manifestation of physical processes. But our modern computing efforts to do things like AI, they're getting better, of course, but I think quantum mechanics quantum computing may allow us to produce something like consciousness in a non-human form.
I would think so, because when we think about the connections of our brain and when we're trying to simulate that with computers, those are still all logical transistors that we're building. But in our brain, we have neurons that have axioms that then go out and connect to a bajillion other things.
Yep.
And then being able to have the different superpositions of the different neurochemicals that then transmit between them. There's a whole lot more that I think that you're 100% on the money with that we might be able to get.
Just
better.
hope all of these things just have a plug. Just one physical thing plugged into a wall.
But we're going to put it in the
Except for
cloud.
Apple. Apple have a different one.
I don't
I don't have a different connector.
I don't want an implant. I don't want to have to plug something into my head.
Oh, I would, if I could have a brain port today that I knew wouldn't kill me, I'd still go for it.
Don't you want to be uploaded to the cloud so you can live forever?
Do you guys remember massively parallel processing back in the day?
Yeah.
Yeah.
That was going to be a huge thing for us, right? And it's kind of fallen away. But maybe with quantum, it's going to come back because...
Yeah, in a more powerful form, I think. That was really all about getting around the limitations of the hardware at the time.
Right.
I actually did, for when I was going to, when I was working on my computer science degree, early 2000, that was one of the projects that I had all these old computers and I was going to like wire them all up in Parallel because that was a thing where people were doing.
Oh, Beowulf clusters. Did you
Yeah,
know those?
Beowulf, that's what I was trying
That was
to
the
think.
Linux
Thank you. Yes.
implementation of the parallelism.
And that was
Right.
all about just
Old
ramping up.
guys, let's go.
Yeah. It was getting around the hardware. I mean, this was Windows 98 days, you know. And,
Right.
And now
the ancient times.
transistors got way smaller and CPUs got way faster than anybody thought. Everybody thought Moore's Law was going to like put an end to things like around
Right.
2003 or something, but we kept finding new ways. But we are going to hit a limit. We're probably close to the limit with silicon-based transistors.
We're 10 years away from figuring out all science. We'll just be like,
They said that in the 90s too.
Every 10 years they say
Stephen
that.
Hawking thought we were just on the verge of the theory of everything. It's
That idiot.
Still out there.
Yeah. We just keep finding smaller and smaller things. We used to think that the atom was the smallest thing, and now we got quarks.
We keep finding smaller and smaller things, but then there's a couple of really, really big problems.
Yeah.
Like the whole general relativity versus quantum mechanics thing.
Mm-hmm.
They're both fantastically accurate, but they can't both be right. So there's really big
that
problems.
might get,
They're very accurate, but
unify-
not right.
Yeah,
They
you
can't
just-
both be right.
Oh.
They're both very accurate in their domains.
Is string theory like rabbit hole that
String theory is a big one.
Is it-
It's
Yeah.
largely
Is it-
been discredited, in my opinion, only because nobody can make a prediction that's testable with string theory. And if it's not testable, it's not. So the minute somebody can say, here's a test that will say that there's 11 dimensions or not, we might be onto something, but the whole string theory was all based on this idea of supersymmetry, where every particle has supersymmetrical, which I'm not going to go into, but everybody thought we were going to figure that out. We were going to find supersymmetry in the Large Hadron Collider in Geneva, like back around 2010 or something. Everybody was like, around the time we discovered the Higgs boson, which was predicted back in the 60s.
The God particle.
But the supersymmetry experiments, all these carefully designed experiments, it never showed up. The supersymmetry never showed up. So I think a lot of physicists think it's not a thing. And without supersymmetry, I don't know that string theory is viable.
So all of those physicists that have devoted all of that time for all of these years.
That's how physics is now. A lot of people are going to spend their whole careers getting nowhere.
Because the
I
mathematics
feel,
behind it is very difficult.
kinship with those people.
Yeah, yeah. It's a lot like programming.
Oh, I just worked 8 months on this project and it's over budget. They pulled the plug. It's all gone.
But
Okay.
yeah, I don't know. There's something now. Max Tech. There's something now where they're trying to. The whole problem is you have to figure out how to quantize gravity, because that's the whole problem. Quantum mechanics in general.
What does it mean to quantize gravity?
So in
Can you
quantum mechanics,
quantize what quantized
Yeah.
gravity means?
Right.
yeah. So there's 4 forces. I'm doing air quotes because I'm gonna turn around and say gravity is not a force. It's a curvature of space-time, which Einstein showed us. So it's not a force. It's just the fact that space is curved. That's why things go. But the strong nuclear force, which binds the quarks together, is a force. The electromagnetic force everybody knows about. It's that thing right there, that power strip, magnetism. And the weak nuclear force, which has to do with radioactivity, all of these things are quantized. Light comes in discrete packets. Electromagnetic waves / particles come in discrete packets. There's space in between them. You can't do 1.3 of a light packet. You can do, but with gravity, that doesn't work. So you would have to quantize gravity. You have to say that space, physical space, is quantized. That means there's a minimum distance. There's a distance at which two things in space can no longer get any closer together because there's a minimum. Gravity. Think of it as pixels. Pixels like a TV. There's space in between the pixels, and you can't get them any closer. Right. Gravity has to be like that to obey quantum mechanics. But general relativity says it can't be like that. Okay. It has to be smooth and continuous. So there's a mathematical discrepancy that's very fundamental to general relativity.
I know what to do now.
And that's why Dan's here.
I'm going to get the smallest ruler I can find. I'm going to find that.
It's called an angstrom. But back to Akila's point, most of physics now is focused on these ever more arcane, like graphenes, like these nanomaterials and stuff. And they're doing cool things, but you've got people that spend 20 years to figure out how to make progress, little incremental progress in this.
Right.
There needs to be some big seismic fracture in the physics landscape that says something is deeply, deeply wrong because these two theories don't play well together.
Do you think if quantum computing and AI get far enough, provide the lever, the wedge?
That's a really interesting question. I hope so. I would love if we could get an answer in my lifetime, not hold my breath.
The first thing powers the second thing. If quantum computing gets to the level that silicon computing is today, then AI will get exponentially better every single time. And we're already blown away with the state of AI right now on silicon processors, right?
Yeah.
It's kind of ridiculous how good it is. So swap out the entire base of that with quantum computing, make that something that's affordable. And who knows if we get there, right? But it probably will.
Depends on how many
I could
suns we need to power it, right?
Yeah, I could see quantum computers being used to extrapolate and quantify the data needed to build the models. Like when we're doing all the stuff to train models, that's where a lot of the effort goes. But when you have that end model and the weights, that's really easy to put on a particular device.
Yeah, but what if you do all of that on the fly with quantum computing, right?
But why would you need to necessarily do it on the fly? I think that we could get to a point that we're using AI in a manner that, like, again, kind of like with the differences in quantum mechanics and general relativity, they're very specified in their particular domain. And so I think that we could get really good at developing AIs for our particular thing, like solving these particular problems, for doing speech recognition, for doing image recognition. But like, we wouldn't necessarily need to solve a general AI intelligence thing that can do everything. Because in that over-specialization of everything, you're losing the efficiencies of specializing in a particular. And that's just as true for humans. We have that problem. If we just try and do and learn everything, be a jack of all trades, we aren't specialists in anything, we don't excel at it.
Thank you.
I mean, that's really true, because you do have to specialize in something. That's why we have the jobs that we have. We've specialized in SharePoint or programming, Java or .NET, or Dan specialized in several things over time, as have I, and your QA, and those are facets of software development that are nice and great. But I mean, if I tried to code in Java, do SharePoint, QA it myself, and do .NET development, it's never going to work.
You just described a day in the life of a startup. Any developer at a startup does all that stuff.
But they don't do it well.
And
they do
forever.
It better because they grow, and then they find people to do those specific things.
They don't do it forever.
Yeah, or they fail and blow up.
Facebook is not currently having one guy do all the development.
Yeah.
Microsoft not having Bill and Paul sitting in their garage working on stolen or purchased software and selling it off. So those things change over time. They do start small, and it's easier for us to conceptualize doing all those things. But I know my QA skills on my code, what I would prefer as the enterprise level of QA.
Have you ever considered just not writing?
Have you considered just being better?
Yeah, have you considered just
the Jutner method?
Yeah.
Just write perfect code.
Yeah.
So I think another area.
Call his team.
I think another area that will probably be hugely affected by, as quantum computing matures is the whole financial sphere. So we've already seen like cryptocurrency and stuff. And if you look at the history of money, it's kind of gone over the civilization, over human civilization from this like barter system, which
that's perfect.
Which has problems, right? Because you have to, In order for me to barter,
100.
All right.
in order for me to barter with you, I have to have something you want. You have to have something I want.
Right.
So that was a big innovation that currency was. It's like we can make things more liquid. I can just give you a medium of exchange, and then you can use it later when you find something you want.
Yeah.
And so now in our lifetimes, money, we've gotten rid of currency to a large extent, and now everything's binary digits in a computer system.
We ditched gold standard to go with
Yeah, we
economy
ditched the gold standard. Cash is going to go away soon. And
Not if they keep charging me 3.99% for my credit card.
well, so that's an inefficiency,
Right,
though.
right.
And the drive with money has been to eliminate the evolution of money is the elimination of inefficiencies. So
We're
quantum
going to have
computing.
to have.
Well,
and this, oh, sorry. Let me finish.
No, we're going to have to. There will be some form. I mean, money will look way different
Yeah.
in the quantum computing era.
Well,
Yes.
you have to get everybody internet and everybody a device. Everybody's got to be plugged in and have the ability to do that.
I mean, that's an interesting thing is that we're dragging behind this other sphere of the globe that isn't we're sitting around a table with multiple computers and devices and text recognition.
You also
and,
have a really large population of cash workers.
right?
And
Say more, but not too much.
and that's going to really hurt them a lot.
What's an example of
But-
a cash worker right now?
Let's say,
Careful.
Let's say if Kyle comes over and helps me out with painting my trailer, and
yeah,
I just give him some cash.
right. Lawn care, snow removal. If you say, hey, will you give me a deal if I pay you cash? You're like,
Is Kylie?
I don't do that. I never do that.
Painting my trailer.
Organic materials.
Well, I mean, again, there are a lot of these things are because of inefficiency, social inefficiencies, or
Right.
inability, like inequalities. Quantum computing will probably help solve some of those problems, but it might exacerbate some of them because of the
It's gonna make it
disparities
way worse.
you're talking about in the short to long term.
Right. Well, I think there's a desire to go cashless. 'Cause money is just it's a battery that holds value, and
And COVID particles.
COVID.
and a lot of COVID.
And it's not a set amount. It fluctuates. It depends
Here's my
on
20.
how much value it's storing. But it's like we try to get like that right. But it's big fluid dynamics like economy system, and a lot of it is unknown, uncaptured.
Yeah.
And they want to capture all of it and know about all of it because then they can tax all of it. And
Well, and what would happen if somebody blew up all of Wells Fargo's servers tomorrow, like every last one of them, all their backups? Where would your money be?
hypothetically,
Hypothetically,
Where would your money be?
well, it's insured by the FDIC.
only up to $250,000.
Which covers me plenty.
But for all the people that it doesn't, I mean, like when
Right.
we're talking about these huge financial systems, and like even just like with how it's going to change, the cryptocurrency world, everything's based off of SHA-256. So like eventually we got that thing where it's like essentially just calculating like really big prime integers, and quantum computing does that exceptionally well of factorizing large integers. It's going to change the way that even just cryptocurrencies as an algorithm, as a blockchain is designed, will need to work to be able to do that. And even if
Because
it's
the
not
compute
just
power right now is ridiculous.
and like so beyond just like breaking the passwords, there's a handful of ways you could tackle that. Because like essentially you could, if somebody's using like say a Bitcoin address and pushing out multiple transactions with the same public, it then for every single public address becomes exponentially more easy to crack that with a quantum computer.
Okay.
So you'd have to make sure you're trying to send stuff out of a new address every single time. If you can also with quantum computing start to guess what the encryption or the password is going to be for new wallets that haven't been minted yet. So you could sit and wait and just essentially get the passwords minted out for all of these new wallets, and when someone walks into it, puts money into it, you can then pull and take it out. And still, even then, beyond just breaking the algorithm, you can still execute a 51% attack where you have the processing power to outcompete the other people mining on it, and you have a like democracy share of 51% to say what the rules are, and you can just take everything.
Like it doesn't it like weight the ledger based on the shares the person has?
Ethereum has moved to proof of stake, where when you're processing a transaction, you have to essentially put forward money and saying, I'm putting forward, 30 Ethereum, and then here's my solution for this particular problem. And it's a group of these people all putting forward their money and checking each other, make sure that everyone is following the rules to then progress things forward. That's one way that Ethereum has tried to solve this problem and produce like longevity in the long term.
Because if you own enough of it, you kind of have enough weight.
Only if you're actually processing stuff. If it's just in your wallet, it doesn't count. You have to be processing transactions and putting that stake up to actually filter yourself. And it still doesn't stop somebody from attaining a majority share of shares in the future by just gathering a bunch of Ethereum.
Yeah.
Hey, Dan, so let's consider I own a small diner in Northeast Minneapolis, right? I make bacon and eggs 1,000 times a day. I process credit card transactions. How is quantum computing going to help me?
I mean, again, making predictions.
Yeah, go ahead.
I think money is going to be radically different in the quantum computing area. I don't know how, but I'm guessing nobody will be carrying around little plastic cards anymore. That's probably...
Are we getting RFID implants into our wrists?
You don't already?
I guess I kind of do.
So I really don't know, but to back up like 100,000 miles, like all of this reminds me, there's always been this question among scientists, it's like, why does mathematics describe our world so well? It's an interesting question. Why should it be such a useful tool? And there's a book by a guy named Max Tegmark, who it's called The Mathematical Universe. He is taking a radical position that the universe is a mathematical object, and that anything that happens can be represented mathematically. And I think he's onto something, and I think quantum computing start making that clear to people, because as humans, we've always set ourselves apart from the world, like we're special, we got created from clay or all this stuff. And yeah, you can predict things like cyclones and rainfall and all this, and that's math, but we're not math. But I think in the quantum computing area, we'll come to find out that we are mathematical objects. And everything we do, including buying eggs and bacon,
don't ever tell Chad he's not special.
What was the name of that author, by the way? That sounds like
Max Tegmark. He's
Well, it's like, why does math fit the
Danish.
world so well? It's because math, came from the world. It's derived from the world. You're counting apples.
See, he flips it around backwards. He says the world is derived from math. The universe is a mathematical object.
What if we are?
Well, it's
still fun.
It's a fair question, but then you have to ask, what does it even mean to be a simulation?
What's the difference?
Have fun with it. Okay, enjoy it. Yes,
right.
There has to be a simulator in that. If we're a simulation, there has to be a creator of the simulation, which is...
Here's a stunning disagreement with that. Okay, you're saying, what happens if there is something that happens mechanically that just, is having this mathematical function? We're all simulated with it. Somebody has to observe it. What if it's just the same thing as us observing quantum states, in that there could be potentially quantum states just happening and nobody's observing them? It's just part of a larger mathematical function outside of the universe that we know.
Yeah, there's some interesting points. And if you read any Buddhist literature, that's another side hobby of mine. There's been a long-standing part of Buddhist philosophy which says there is no ego. The doing is the thing. There's not an ego that does things. There's just the doing. Mm-hmm. And the doing and the doer are the same thing, which has profound implications if you think, because it means there's not this little self somewhere controlling everything. There's just processes unfolding.
So video games, are they going to be cooler with quantum computing?
You're already in a video game, right?
Okay.
My assumptions for trying to guess crystal ball in the future about how it could improve video games. Quantum computing used in models that will help workflows to help build the game. So AI models that can generate textures, generate buildings, generate specific things in a workflow that can then be used by designers, developers into something that you can play. It could be used for modeling or simulating the AI behaviors of the things that inhibit that world. They give them their rule sets of what they're able to do. You're a cube that rolls around, and this is what you can do. Now we're going to try and put make it feel a little bit more, respond to you in different ways.
So it's the tool to build the game, but the game is still going to run on a regular computer.
Yes, because I feel like the question of solving for the problems of quantum computing, which is really expensive, and the measurement of trying to actually measure the quantum events is going to be so explicitly prohibitive that it's mainly going to be used for extrapolating and explaining large amounts of data and then using that model in classic.
So, have you had a project in the past, throw out to the group, that had a problem you had to solve that was very difficult, that looking back you would say, wow, if I only had a quantum...
How to get a screen reader to read out the error message on a React component.
Okay.
One thing that I would say that is more quantifiable problem, not something that necessarily I worked on, but something that is a practical implementation of this, say with Google Maps and translating the closest or the best get to where you need to go. Calculating in all the environmental factors of traffic, things like that, of knowing the best way to get you to your end goal, meeting still a set of criteria. They've also put in like green paths, so knowing which way would save you the most fuel or things like that.
Most efficient, right?
So there's so many different variables in this to try and quantify in between these two indiscriminate points on a 2D plane of like what's the best way to get there and what are you able to do in your type of vehicle. That as you start switching between these, this problem gets to be a lot more difficult, and a quantum computer could do that a whole lot better than trying to do
there's been a lot of, manufacturing is a place where a lot of that comes into play, because you're always trying to measure and take a lot of data and put it together to make things faster or better or, different. And so the few manufacturing things that I've done have been nice to have be able to capture more data and process more data and things like that.
What about some of the really big problems? Like, what if the Earth really is heating up, and what if we're heading off a cliff right now? Like, can quantum computing help with some of those problems?
I think quantum computing is going to help model those problems.
It's not a quantum problem; it's a people problem.
And model the solutions that we want to try.
It's a people problem.
But
That's the kicker for me, is the word model. Doing science, getting your science on, and doing science based on a model hinges on the quality of the model.
They're not building full-size jets anymore and then making sure that they take off and fly, right?
Yeah. But I'm not saying that models
is a bad word.
Ruin everything.
Right.
But the quality of the model, is that something that quantum computing, AI, will be able to do?
That's something I
create
expect.
the model for us.
And so when we talk about AI and machine learning and things like that, the models are not descriptive in that it's fitting in this tiny box. When we started doing the generative AI topic and talking about large language models, there is so many hidden layers in those that we have no clue what they do when you're generating those. So the models, as they're building and optimizing them to give you something that you can then implement. And when we're working with these large data sets of taking in 1 trillion parameters of words and knowing the weights of the likelihood of them being next to each other and not understanding because that's an anthropomorphizing of it, but having the correlation of the probability of these things being together, it is something that's not determinate, and there is so many hidden layers. So when we say a model, it's not necessarily saying it's going to be a model of a 2017 Acura where it will be pretty much one of a few different iterations of that. It's going to be more so every potential car possibility put together, so long as it still fits the descriptor of a car.
Right.
I think with a lot of that stuff, though, what if we had a perfectly sound scientific solution to global warming? What have we learned in the last 5 years? If we say, hey, trust the science, what do we do?
That's a challenge.
We have to weight that with human value. What we value as a society as far as convenience, what we value as a society as far as what we want out of our lives and how we want to go about living. So we have to reconcile that, and I think that AI can help us reconcile the differences of how can we maintain our quality of life or the way that we're going about things while still addressing the problems, or at least maybe instead of stopping global warming, if that is impossible, how can we best adapt to the way that we're screwing over the planet?
To me, the term trust the science, it's if you do that, it's no longer science. You can't completely trust because things might change.
That's
right now. This is what we know right now.
But that is science.
But that is science. That is the definition of science.
But it's trusting what we know right now as being the thing we need to do. This is the answer. But then down the road, we realize it's not. Butter is fine. Margarine is horrible.
But if we never take the step forward and if we never make any mistakes, we'll never move anywhere at all.
Have you ever looked, so you know chaos theory, right?
A little bit about it.
A little bit, yeah. I think quantum computing, quick chaos theory is basically the Jurassic Park model, right? Remember when Malcolm's in the Jeep and he's like, look at that raindrop, right? It's going to go this way or that way. We don't know. right? Because there's too many variables.
Right.
But I think with quantum computing, the ability to model every single variable going into every single little thing and actually form accurate predictions, so chaos theory becomes
Just
Less chaotic.
Yeah. Although you will run into like quantum mechanical phenomena, like the fact that like for any given particle, it's a probabilistic system, right? You can never specify exactly what a particle will do. Quantum mechanics doesn't let you do that.
But you can nudge things to change the probabilities. Like lasers and microwaves are used to do that.
Yeah, I'm just saying that like I think quantum mechanics, just the world we live in, may prevent us from ever being able to precisely specify. We can't even precisely specify the state of a simple quantum system. You can get a probabilistic description of it. And for a lot of things, that's fine. Like a balloon has a certain pressure and a certain volume. What we call the volume or the temperature of that balloon, temperature is not a quantum mechanical thing. Molecules do not have temperature. Atoms do not have temperature.
Right.
When they move faster, we recognize that as heat.
we measure it as
It's a probabilistic thing. Heat is a probabilistic descriptor. We're saying on average, in this balloon, these things are moving faster because it got warmer, and I can feel it. But to say what every molecule in that balloon is doing is prohibited.
Right. But Chad is saying that if it can know every single thing, you know what way the drop is going to go. If we know every single thing about the planet Earth and every molecule that's moving around creating weather, then we can accurately predict what's going to happen next.
The biggest problem is knowing everything and how we measure everything and how we quantify that data and put it into never get to the point to quantify that volume.
I was able to convince my niece that I know everything. So I'm there. Yeah.
parting thoughts, Peter.
Thank you, Chad.
I think it's going to be amazing. I think it's going to be maybe not life-changing for us, but life-changing eventually. Sort of like the computer. If you looked back at ENIAC or any of those computers that were the size of rooms, and you look at today's computer, it's the steps are there. We've seen them happen, but to look from one to the other without knowing those steps, it's just impossible. So I think it's going to be amazing. I hope it's going to be amazing. It could just be nothing. We'll find out.
It's so far over my head that I'm looking like, because I talk to ChatGPT and it tells me, and I just believe it, and I believe Wikipedia, and I just so I'm just waiting for the AI to tell me what to do. I'm kidding. No, I hope it revolutionizes a lot of the problems that cross all businesses, like knowledge capture and content handling, content organization. There's stuff that we talk about that we really have a hard time pulling off. So if we can have like this prosthetic assistant watching what we're doing, processing all of that information, and then making that available, and then we just tell it what we want and it can give it to us, it's going to save us like a crap ton of time and make us more efficient. Like your IntelliSense stuff, what if it's IntelliKnow? And you just like, I need to do this. Okay, now I need to do this. Boom, you're talking to it. It's Jarvis. That's kind of what I'm hoping for. I'm hoping I can build Iron Man armor by just telling Jarvis to just build Iron Man armor for me.
So as somebody that is a software architect that chooses to focus specifically in quality and how that practical implications are, I'm interested to see how it's going to end up impacting companies and the need to switch off of RSA eventually, and what that impact is going to be on legacy systems that don't have the capability of stepping out of that, and wondering when we get to a point that we have a quantum computer in the cloud that's able to run Shor's algorithm to a point that it can actually break RSA encryption relatively easily. I want to know what the implications of that is, what the problems are going to be for companies in migrating to newer systems that can actually implement algorithms, integrate cryptography that is hardened against quantum. And from just a quality and quantum space, I'm very interested to see the ways that we continue to iterate and solve some of the problems that fall out of. There's some work being done in topographical qubits. There's work around trying to take qubits and essentially have multiple physical qubits represent a single logical qubit using Shor's code to like quantify and mathematically model or understand when things are falling out of alignment. That has a lot of overhead, but like understanding the ways that we end up implementing quality in quantum architecture, like the stability of that. I'm excited to see how those continue developing.
As a consultant that builds clients to help solve these problems, I'm also excited to stay on top of them so that this is just one big Y2K problem coming in a decade or a generation.
You're right, it's coming and we see it.
It's going to be a thing that we're going to have to actually retrofit into state solutions to some degree, right? I'm very happy to be working for a consulting company right now that lets us stay on top of all these technologies and all these problems and gives us space to explore, solutions to the problems. Mm-hmm. And I'm really excited to actually help our clients find a solution to what this is eventually going to be. And I saved the last parting thought for Dan and as you're giving your parting thought, sir, just in mind that I'm a 48-year-old man that had 3 drinks. So,
so way back in the early days of quantum mechanics, Richard Feynman, who's a spiritual hero.
Oh my God, hang on a second.
Famously said that nobody really understands quantum mechanics, and they still really don't. We know the math, and the math works. We don't know why it works. We don't know what it says about the world we live in. I'm really interested in what it says about the world that we live in, and so I'm really hoping that the general relativity, quantum mechanics, irreconcilability problem, I'm really hoping it can help us break current physics, because something's really broke, and usher in a new era of physics. I would love to see that in my lifetime.
Because physics is basically stuck.
It's stuck except for these incremental little super niche fields.
Right.
But the really big problems that have been around since 1905 are still there. So I would love to see some progress there. I'm more interested in what it can tell us about the world we live in than about practical applications right now. And I'm also curious, every technology is a double-edged sword, right? So there will be malicious uses for quantum computing, and I don't know what those will look like, but I think we need to be...
It looks like Kyle wearing an Iron Man suit. That's what it looks like.
And manipulating the global economy.
That's
from
right.
Your Apple keyboard.
What I really am excited about is having...
Are you doing a bonus?
I am, because this is a more serious one.
We'll fix it in post.
Tools that let someone like me do even more awesome stuff that I can do given my current tool set.
I'm excited for the ramifications on the sports betting industry.
I'm going to start breaking every single Bitcoin wallet, starting from the biggest one.
There we go.
I just want to be able to share pictures of cats faster.
I'm not going to take a second scoop.
All right. Well,
Happy 100.
Congratulations on 100 of these. Happy 100.
There should be 100 episodes of hard hitting.
I think we'll say goodbye, everybody.
Goodbye, everybody.
Bye, everybody.
Solution Design Group is a digital product consultancy in Minneapolis. Check us out on the web at solutiondesign.com or look for us on Facebook, Twitter, LinkedIn, and Instagram at Solution Design Group.